everybody. Let's welcome you back to our session number 4, which is product circularity and life cycle analysis. So I'm going to try to keep this on time and rolling. We have 4 wonderful speakers in this session, and I would like to introduce Dr. Jane Wood from the University of Manchester. If I am correct, Jane, you got about over 18 years of expertise working on textile and finding sustainable materials to give them a final touch. So without much more introduction, I would like to welcome Jane to give her talk.
Thank you. I'm very passionate about the textile and fashion industry, so I have to use notes because I could talk to you for about a week. And while that'd be fascinating for me, it wouldn't be fascinating for you, so I'll try and keep on track. So I'm Dr. Jane Wood. I haven't been in academia for the whole of my career. I spent quite a long time in the textile industry internationally as an industrial textile technologist. It was a fabulous industry. I got to travel all over the world. I got to live all over the world, all on company expenses. It was amazing. And I worked on anything from car airbags to Chanel jackets. So I've had quite a diverse career. And one thing I'd like to start off by saying is that when I say the F word, fashion, the C word, clothing, or the T word, textiles, lots of people automatically go to that part in the brain where they say, well, it's just a creative thing. It's very catwalky, particularly fashion. It's catwalky, it's creative, it's design. And I'm here to tell you it's so much more than that. It's so heavily science-based. I was talking to somebody, I won't repeat exactly what they said because it was impolite, but what they did say was without science, we'd all be sitting here naked. And they're right. So just to give you a little bit of context to the industry, it is a fantastic industry to be part of, but there's a real dark side to it as well. So you can see from the images on the screen, we are feeling quite smug as a society at the moment, I think, because we're all getting into our recycling. I'm here to depress you. So if you think, well, I've had a big clear out of my wardrobe, I'm going to donate it to charity, I'm going to send it to recycling, I'm going to make sure that it's repurposed. Statistics, between 10 and 30% of clothing that you donate to charity shops actually gets sold in that shop. And the rest of it goes out somewhere else, somewhere we can't see, somewhere where it's out of our line of vision, out of sight. We've done a good thing. But what generally happens is it gets parcelled up and shipped off somewhere around the world. So the image that you can see on the screen there of the clothing mountain is a landfill in Ghana. What is really crazy about the fashion and clothing industry is that fashion is all about expression, and we change our minds all the time, and we want to communicate different things, and those moods change and those feelings change, and we change as people. So fashion is about changing our minds all the time. Fashion is about us changing our clothing. What might have suited us last year might not suit us this year, might not suit us in 5 years. But we make this clothing out of material that lasts forever, which is just mind-blowing to me. If we don't want our clothing to last forever, why do we make it out of polyester? Why do we make it out of things that last forever and ever and ever and end up in landfills like you can see on the screen? So as an industry, we like to pollute the land by dumping our clothing in landfill. But we don't want to stop there, do we? No, of course we don't. So then we like to pollute the atmosphere as well. So there is lots of research now that is emerging around areas of heavy textile industry, particular areas of China and of India, where we pump so much pollutants out into the air through textile manufacture. So this isn't clothing, this is actually making the fabrics themselves. We pump all that out into the air, goes into the clouds, comes down as rain, gets into the soil, we end up eating it. There's really high levels of really nasty diseases, respiratory diseases, gastro diseases, cancer. Have I cheered you up yet? Wait for my next one. So we're going to go for the hat trick now. So we enjoy polluting the land, we pollute the air. Let's not stop there. Let's pollute the water as well. So it's often seen as an urban myth that if you want to know what colour is going to be fashionable on the catwalk next season, look at a river in China or India. It's not an urban myth, it's true. So lots of rivers are really heavily polluted with synthetic colourants that we use in the textile industry. So while I started off a couple of minutes ago, so it's a fabulous industry to be part of. It's fabulous for killing the planet as well. So maybe it's time for us to think about changing things. So as an industry, we are starting to think about change. We're thinking about quite traditional methods of change at the moment. So we'll see lots of things around recycling. I've just impressed us all about that. Repurposing clothing. There are a lot of big brands now saying, okay, what can we do? There's a little bit of quite a lot actually, greenwashing going on in the industry. But we're thinking about companies like you can see on the screen, like Patagonia, who are using this business model of saying, well, we want you to buy our product and we want that product to last forever. So we're going to educate you in how to make it last forever, how to look after it properly. If it gets torn, we're going to educate you on how to mend that tear. If the zip goes, that's not the end of the world. You can replace the zip. The garment doesn't have to go in the bin. So they're educating consumers about mending their clothing, but they're also saying, okay, well, if that clothing, you can't repair it or you don't want to, send it back to us and we'll do something with it. So they're not repurposing everything, but the majority of their clothing is staying in the supply chain, which is great. I've been dying to say this all day. So we've talked a lot about jeans today, and here's some more. I even wrote it on my book, don't forget to tell the jeans joke. So these are the iconic Levi 501s. So Levi's are maybe greenwashing a bit, but they're talking about, okay, so we're not going to rely on virgin fibre 100% of the time now. We're going to look at how we can recycle, how we can reuse and repurpose some of the clothing that we've put into the supply chain. So they're all really exciting things, but they're a little bit not thinking outside the box. And this is where the industry really does need to change. So now we're starting to think about biotechnology and how that can help us. And I knew I'd get to this point, and I have to take a little pause for reflection. So I have been in the textile industry all of my working life. I studied textile chemistry as my undergraduate degree. When I was at school, I hated biology. I despised it with a passion. I thought it was the most boring subject in the world. And the minute I could drop it, I got rid of it. It's a bit insane that I'm standing here with a PhD in microbiology, understanding probably most of what's been said today. So well done to me. So this is how biotechnology is starting to change the face of fashion. My own research work looks at bacterial cellulose. So lots of people have looked at bacterial cellulose as maybe a purer version of cotton, thinking about how we can use that. It develops as a biofilm, so we thought about it a lot as replacement leather. And that's kind of one of the problems with biotech in textiles. We think about it as replacement, and I'll come back to that in a minute. But some of the images you can see on the slide are looking at mycelium and how that can be used as a replacement for leather in the industry. Mycelium has been used quite successfully in handbags, in upholstery, in car interiors. The image that you can see down the bottom of the screen of the garments is actually a collection from Stella McCartney. I'm not Stella's biggest fan, but she does engage quite well with some of the biotech space. So we've got to ask ourselves the question that if we can do this, why aren't we doing it? There's lots of industry interest in being more sustainable, being greener, thinking about how we can change the face of fashion. But there's a few reasons why I think, and lots of other people think, why it's not taken off just yet. So one of the things is we're terrified of anything new. So as you see, we like to go on the traditional routes of cotton, wool, polyester. We like to stick with things that we know. These are really novel, different things that we've never really experienced as an industry before. So it really is a case of working with a lot of designers and product developers, feeling our way through these things. The other thing is economies of scale. So we like to produce a lot of textiles in the fashion and clothing industry. And some of these novel things like bacterial cellulose and mycelium, economies of scale aren't quite what they should be. But then you could argue that maybe one of the big issues with fashion and textiles is consumerism, this demand for more and more and more and more. So maybe we should put that thought to a side and say, we don't actually need loads anymore, we should just start small. But one of the biggest problems that we've found with mycelium and with bacterial cellulose is because we're thinking of them as replacement leathers, the default setting is, well, let's test them against animal leather. Let's see how they perform. And they're not comparable. They don't perform in the same way. And that's kind of where these sort of innovations are starting to fall down. So I think one of the big things with biotech in the fashion and textile space is that we need to think about these things as new products, exciting things that can give us this whole host of different properties that we haven't got in our traditional textiles. And I think until we start thinking about these new things in that way, I think we're always going to struggle. But then the other thing that we're starting to see as well is how biotech can help us not completely make the leap from our comfort zone, but maybe help us with some of the processing of the traditional textiles that we have at our disposal. So I was at a very, very exciting event in Glasgow a couple of weeks ago where there were lots of people talking about loads of great biotech stuff. So some of the images on the screen there, the top one is looking at how we can extract dye from algae. There's lots of work around using microbial activity to develop dyes. So that's reducing our reliance on synthetic dyes that are really harmful to the environment and thinking about how we can get more biodegradable, more sustainable things in the product life cycle. And then the image there of the knitted fabric and the Petri dish is to remind me to say that there's some really, really exciting novel work going on about extracting fibres from seaweed. Elastane is a big part of all of our lives. And if anybody in this room wants to say they're not wearing elastane, put your hand up now. Good, sir. Everybody's wearing pants. Great news. Because elastane is what keeps your pants on. So we're quite beholden to it. So to find a bio-alternative to that chemical elastane is really exciting. So it's a really exciting space. There's lots of people that are saying that seaweed is a renewable resource that's almost carbon negative, which is quite exciting. That's a little bit out of my knowledge zone, I have to admit. So there's loads of exciting stuff going on. The other thing that biotech is really helping us evolve in the textile industry is thinking about, well, okay, can we develop some of the traditional stuff but in a lab-based environment? So the T-shirt that you can see, the black parts of the T-shirt are grown in a lab leather by a company called Modern Meadow. So very similar to the lab-grown burgers that we can all get now. The image in the middle is inspired by spider silk, a company called Spiber. That was a garment that was made for North Face. So we can see that these products are really starting to be on the cusp of the mainstream, and it's really an exciting time to be part of the industry. And then something that's really starting to change the industry and as well in terms of manufacture is 3D printing. So looking at different materials, biodegradable materials that we can 3D print with will be a real game changer. But at what cost? So when we invented synthetics in the textile industry, it was seen as a revolution. So we thought that we'd created something that was going to change the world, and it did. We thought that we were going to reduce our reliance on farming sheep for wool, on over-farming the land for cotton. And in theory, yes, we did, but we kept farming sheep for wool. We kept over-farming land for cotton. So synthetics kind of became the things that sat alongside natural fabrics. Synthetics did revolutionise the industry because we got better dyes, we got better finishes, we got all these textiles, the drip dry shirt, the dress that you could throw in your washing machine, half an hour later it would come out, half an hour later after that it would be dry, you didn't need to iron it. It turned us all, men included, into domestic goddesses. So we didn't have to bother about our clothes so much. It totally revolutionised the way that we saw clothing. But what we didn't do when we invented synthetics, and I'm talking fibre and dye, is think for 1 minute of the impact that we would have on the environment. So now, as I showed you at the beginning, we have these piles of clothing that just aren't biodegrading. But the worrying thing is, if you look at some of the research on microfibre, which is also a problem with synthetic clothing, a lot of microfibre isn't polyester, it isn't nylon. A lot of microfibre is cotton and it's wool. And it's because it's so heavily synthetically processed now that it's just not biodegrading anymore. So it's not behaving as a natural anymore. When synthetics were invented, though none of us saw the consequences of these actions. So for me, even though it's a really, really exciting time to be in biotech and to think about all these new novel alternatives that we can have to natural traditional textiles and the synthetics, I think we just need to be really careful and say, at what cost? If we're thinking about biodegrading all of our clothing tomorrow, do we know what the impact of that will be on the soil biome, on the gas emissions from that clothing, on all the different things that it's going to affect in the environment? And I don't think we do yet, and I don't think we're quite there yet. So while we're keen as an industry to make the change and stop being so polluting, I think we need to be careful and work with partners in biotech to take it slowly and think more carefully about what we're doing. Thank you.
Is working, but I shout. I got a good voice. Thank you, Jen. Very good talk. Anybody got any questions for Jen? I do.
It was just to the point of, so I did my PhD in spider silk fibers, so I'm really into that. So the North Face jacket that you showed was about 2% spider silk.
Yeah, it was.
Yeah, that was absolutely.
Yeah.
I mean, a label was
Yeah.
silk sort of thing. So that's the point of the greenwashing element.
Yeah, it is, absolutely.
The second part of the same point is that the blends that we use, so cotton with polyester or any kind of new and perhaps more sustainable fibers that you blend with silk and polyester makes sort of both routes of recycling unfeasible.
Yeah, it does.
I suppose what can be addressed by design? How can we solve the problem by design?
I think as well, to add to that, the other problem is when we talk about recycling clothing, there's so much more to it than just the fabric itself. So the threads are often different. There's zips, there's buttons, there's labels, there's prints, there's embellishments, embroidery, beads, sequins. I could go on for a week. What's the answer? I don't know. I think thinking a bit more cleverly about design. So for me, I bang the drum of fast fashion. I don't think there's anything wrong with fast fashion as a concept. I think the problem with fast fashion is making things that last forever. So I think it's being more mindful in terms of circularity about what's happening to that clothing or where it's going to end up, what it's going to end up going into. So for fast fashion, if you made something that was going to be almost useless because it had biodegraded in 6 months, it doesn't matter because you're not going to want to wear it for more than 2. But then I think with the blends, if you're thinking, well, that's going to go into a product like the Patagonia products that are going to last forever, they become less of an issue. So I think at a development and a design stage, we just have to be more mindful of how long do we want these products to last. And if we do want to disassemble them, then brilliant, but design for disassembly. That's what we need to do.
So I do know that when you talk about recycling, excuse me, what I've got called. When you talk about recycling, oftentimes we have secondary pollution as well. So if you make a product and talking about recycling it, but also the process of recycling, there's still the aspect of releasing the secondary pollution to the atmosphere. So how do you balance all of this at the end of the day?
When we work that out, we won't be standing here. We'll be on the beach in the Bahamas. I genuinely don't know the answer. And it comes to mind as well that we were having a conversation. Sorry, this isn't biotech. This is a bit more about recycling and clothing and talking about the consumption thing and saying, well, we need to stop buying new things. There's some stats floating around that there's enough clothing on the planet now if we stopped tomorrow and didn't make another thing, we have enough clothing on the planet to clothe the next 6 generations of people. So, well, then we have to change that mindset of consumption, don't we? And, we're talking about, well, if we reuse and recycle, you're right. What's worse, reusing and recycling and the pollution that's caused against making new stuff? I genuinely don't know what the answer is, but it's a really difficult one. Somebody much cleverer than me.
Mine is very quick, but I probably will wait for the answer when we get the next break because we're over time. But it's more about the presence of the Northwest or England in general, about recycling clothing or using different feedstock to produce more renewable type of clothing. So how advanced are we in the market at this point? Everybody that is here knows that I'm very linked to the brewery industry, and I know there is a company in London that uses BSG to produce fox leather, and I would like to know about that, but we can discuss it. Thank you, Jen.
Thank you.
Our next speaker, super happy to introduce Dr. Rosa Cuellar Franca. Probably the only person that can pronounce that name right. It's me. Rosa is a doctor in chemical engineer with over 15 years of experience in sustainability and life cycle analysis, trying to mitigate our carbon footprint. So, welcome, Rosa.
Thank you, Ale. Thank you very much for having me here today. And what I want to talk to you about is life cycle assessment, what it is, and what it can do to help advance innovation in this very exciting field of bioengineering and biotech. So yes, the title of my talk has the word innovation in it because I want to demonstrate through a few case studies how this tool can help you from the very early stages of process development to understand what are the opportunities that you have to make your process better, or what are the things to avoid and perhaps change direction early on rather than wait until the end. So it's been really good to hear that life cycle assessment has been integrated in the work that I've been hearing this morning. I've heard the word carbon footprint, so that's really good. It's good to know that this is already in people's minds. So let's start with, for those of you who are not familiar with life cycle assessment, I just want to spend a few minutes to explain what it is, just to make sure we're all on the same page. So under sustainability, we have 3 pillars. So we have the environment, economics, and social side of sustainability. And LCA tackles the environmental side of sustainability, and it's a tool that will enable us to quantify the environmental impacts that human activities will have in the environment, and it covers multiple environmental impacts, so not just carbon emissions, not just greenhouse gas emissions, it covers so much more. But because of the relevance of and the global challenges and the targets that we have, we keep hearing more about carbon footprint. But it encompasses more than greenhouse emissions. But it's an environmental management tool. We have standards and guidelines. There is a proper methodology in place, as you can see in the diagram there. So it has steps that we need to follow. But basically, it applies the principles of life cycle thinking. So we not only focus on the activity that we're interested, but we also think about what comes before and after our activity. So we take into account the very origin of the raw materials that we use, how is the electricity or the energy source or generated, what happens afterwards, and that depends on the scope of the study, of course, but just to give you an idea of what we mean by the life cycle thinking approach, and that's why it enables us to understand unintended consequences that our activity or our process may have. And it will translate burdens into environmental impacts with the use of models developed by other stakeholders within the world of LCA. So there's a lot behind the model that we work, but as practitioners, we make use of the tools available. But going back to the system boundaries, here we have a very generic example of the life cycle of a typical chemicals process. So we can go beyond the production and look at the application, the end of life, if there's any circularity involved, or how do we account for that recycling loop, etc. So the scope can vary, and that will depend on who's commissioning the LCA, what is the purpose of it. And among the most common applications, well, we have the comparison of two different alternatives. We might want to identify what is the key bottleneck or hotspot, as we would call it. We want to understand improvement opportunities, but we can also use LCA as a design tool, as I was saying before, that it can help us drive innovation towards the right direction. We can use this, especially in this landscape, as a feasibility study to help us understand what are the opportunities there. And very important, it can help us shape and direct policy. So in the next few minutes, I'm going to give you some examples that touch on these common applications based on work that I've done with some people in this room, actually. So that's good. Okay. So the most common application, a comparative LCA study. So this is shifting a little bit away from the biotech space, but it's important because of the implications around existing technology and infrastructure. So I worked a lot in the carbon capture field, and the main driver is, well, mitigating climate change. So we're looking at best ways in which we can capture CO2, and for that we need solvents that might not be very good for the environment, so we're looking at alternatives. So this study was looking at alternative solvents for CO2 capture, and I've been working a lot with people that develop ionic liquids, which are alternatives for organic solvents, and they have a lot of advantages in the sense that they're tunable and they might require less, milder conditions to operate. So we wanted to look at what would be the implications of deploying an ionic liquid for CO2 capture, but looking at a larger scale, what would happen if we would implement this on a large scale and look at a hypothetical process. So we rely on techno-economic studies out there, and there was an ionic liquid that was reported that could capture higher concentrations of CO2 compared to MEA. So we looked at the full life cycle of that. And when it comes to, let's see if I can find it out. So when it comes to the amount of solvent that you need, yes, ionic liquid performs better because it has greater absorption capacity. But going back to what Jane mentioned, at what cost? In order to increase the absorption capacity, we need to work at higher pressures, so that's going to increase the energy demand for capturing the CO2, and that's why we can see, so the dark purple bar that represents the ionic liquid in this graph. So we can see that in order to increase that uptake in CO2, well, we're going to have to pay a higher energy demand. And the result, both the MEA and the ionic liquid, will bring down the emissions of this power plant that is generating electricity from coal. But the performance of the MEA is still better compared to this ionic liquid. But it's not all that bad. We learned a lot from this study. So I was working in collaboration with researchers that designed them. And when they're designing them, they think about the task. I want an ionic liquid that is going to capture greater amounts of CO2. But when we expand the boundary of the system, and we start looking at the practicality of what it would take to deploy this alternative solvent in a in a power plant capturing system, what would it take? So it turns out that yes, those perceived advantages, well, there could be a weakness from a process development, but that's if we assume we're working with existing infrastructure. So we need to rethink that, well, maybe ionic liquids will be better suited using different type of infrastructure that we don't have there yet. But it just helps to think about beyond the task and think about the implications of that. So it was a very interesting study, and a lot of things would learn from a molecular design level. So, okay, maybe we need to work with better capturing, but at lower pressure. So how do we do that? And the advantage of ionic liquids is you have endless possibilities of combination. So that was a very, very insightful study. So that was very good to see that we could have tangible outcomes from that. So that was interesting. And now moving on to the biotech side, I was collaborating with some people in Brazil that were looking at microbial derived colorants. And again, touching on Jane's presentation, yes, there is a need for better sources for colorants and feedstocks that are used in various industries. So colorants, it's very important in textiles, of course. So looking at alternative ways, and here we were not comparing it with the conventional colorant source. So we were looking at how can we improve the process that was being developed, and we looked at understanding the different steps, what it takes to grow and extract this colorant from microbial sources. And yes, so we found that the cultivation step was the hot spot, and it turns out that, well, the cultivation could be shortened. So there was no particular reason why 7 days was the needed cultivation. They just thought it was, well, gives good yield, but this helped my colleague rethink a little bit the protocol for their process. So they still got really good yields if they reduced the cultivation to 5 days. So those were actionable things that they could implement to bring it down. And then we explored alternative sources of energy depending on what was available in Brazil. So that can help us understand the opportunity. So then that shifts the burden to the extraction stage, where the extraction now becomes the hotspot. So the cultivation is no longer a potential hotspot, but now we need to think about, okay, what better solvents can we use? So again, it's a way of understanding what are the opportunities of improvement within the development of the process, and by applying LCA early stages, it can give you that way of understanding the opportunities and implement them early on rather than wait until the very end once your process is developed. Again, the more advanced the process is, or the readiness level of the process is, you get better data. But even with early stage data, lab scale data, you can get very helpful insights into what's going on in your process. From an environmental point of view, of course, economics play a very important role, and that's something that we work in parallel as well. And recently, we work with Neil Dixon's group. You're going to hear more about it in the next presentation. Colleague Micaela is going to tell you a little bit more about this process. But here, the role of LCA was to help understand what was the feasibility of this new valorization technology that was being developed, and using lab scale data, well, understanding the process at a lab scale data, we were able to predict through a prospective study what would it take to scale up this process and what are the advantages with respect to the current fate that waste was having. So we compared with, if we were not to valorize this way, we're going to end up incinerating or landfilling it. So what are the advantages for the gain? And as you can see in the purple bars, we can see that the gap is quite big, demonstrating that there is a potential for this technology to be a better option, and therefore should be more efforts into investing in developing this type of enzymatic valorization pathway. So again, it's giving some insights on what are the hotspots, but also the opportunities. So finally, I want to touch a little bit on policy. And the important thing here is that, well, life cycle assessment is going to give a lot of different metrics, different results, but it's understanding what's behind those metrics, how were they calculated. And something that is limiting innovation a little bit from a policy side is that there's so many guidelines, so many regulations out there when it comes to understanding bio-based processes, and there's so much out there that can become a bit limiting and discouraging. So we, with some colleagues around the UK, we established an LCA network in collaboration with the Department of Energy Security, and to understand what are the gaps, what are the limitations, how can we help. And we established different working groups where we're addressing different questions. So I'm working under the bio-based and upcoming materials working group, where we're looking at, okay, what are the guidelines, standards that we need to assess that will enable a fair comparison between bio-based and fossil-based materials, because, well, we have the disadvantage of scale, technology maturity, costs, and so on. So how can we make that fair? And as I said, there's so many guidelines out there, and we're combing through them and understanding what are the bottlenecks, the gaps, so we can have fair assessments. And also circularity is another big issue, because with circularity you have a waste that it's been generated in a different system, and suddenly the second system, well, is it burden-free, that feedstock that used to be a waste? No, it's a valuable feedstock. Who shares the burden there? So there's a lot of discussions there, and we want to understand, well, how can we enable a fair assessment there? So there is some work that we're doing in terms of helping policymakers understand that, well, the guidelines that they put out there, they have to be in they need to be synced with what is actually happening out there. So with that, I would just like to summarize a few points that a life cycle approach is an important approach to help us understand the unintended consequences that different technologies may have. So you might want to mitigate climate change. Well, you have to ensure that you're actually doing that and you're not just shifting the burden later on in the life cycle of that particular activity. And that LCA is very versatile, and it can be applied to different systems. And as I said, it's a powerful driver for innovation, because it helps us understand where are opportunities for improvement, but also where we shouldn't pursue as a potential solution. So thank you very much.
Rosa, any questions for Rosa?
Do you think this tool could have a lot of value in optimising existing and other than just novel innovation?
Can you repeat the question? Sorry, I missed the first bit.
Do you think that this tool would be really useful in optimising existing processes as well as innovative?
Yes, sorry, I missed the word tool. Yes, so this is something that can be applied to something that you already have. Yes, understand how can we improve something that it's already in place, understanding what are your hotspots. So talking to some people that were developing a new delivery system for milk, they wanted to, replace the lining that they were using, but it turns out that wasn't really a hotspot. So it's like, why do you want to make changes there when you have other opportunities that are going to increase reduction? So yes, it's something that can be applied to existing or push novel technologies. Yeah, thank you.
Any other question? I have a tiny one.
Yes.
How can we use the LCA to help small and medium enterprises to innovate improve their products when their income might not be the same as Unilever.
Yeah.
Because the economic struggles are different for a small one and a big one.
Yeah.
How can we use the LCA to help the small ones to be more sustainable, but without creating economical burden for them?
Yes, no, that's a very interesting question because large companies will have dedicated LCA teams. So universities have ways of supporting small, medium enterprises. So, for example, the Henry Royce, we work closely with them. They have an initiative where they support small and medium companies to help them get that advantage, that edge that they need to validate their product or their processes to show that they're competitive. And that's something that we keep hearing this morning. So yes, so I would say reach out to your local university, see how they can support you. But yes, I think that's where the value of working with academia becomes very, very important.
Thank you, Rosa.
Yeah.
Our next speaker is Dr. Micaela Chacon, another name that I can pronounce. Dr. Micaela is part of the Professor Dixon group, and her expertise is on the use of waste stream to make valuable products using microbes, communities of microbes rather than individual cells. Kind of, okay. Attempt to been there, done that.
Perfect. Right. Thank you so much. Okay, so today I'm actually going to tell you a different story from what's in the agenda, but hopefully you will find it equally as interesting. I'm going to tell you about some recent work we've been doing in the Dixon Group towards the development of a microbial process to produce anisole, which is the structure you see here on the screen. And so the first question is, of course, why? Why are we interested in making anisole? And the answer is because it belongs to a broad class of chemicals that quietly play a very foundational role in industrial chemistry, and that's solvents. So solvents represent a substantial and often unavoidable footprint of the total material footprint of a chemical process. And being able to move away from the current classic solvents that are used in industry towards greener alternatives is a powerful lever that we can pull to improve the sustainability of chemical manufacturing. And so anisole, among green solvents, ranks very well on solvent sustainability guides. It has good toxicity, low toxicity, it's biodegradable, and it has a number of really valuable solvent properties. It's been shown to effectively replace chlorobenzene, which is a toxic solvent in the manufacturing of thin film devices like printed electronics and photovoltaics. In addition to being used as a solvent, it also can be used as an additive or an intermediate in the pharmaceutical or the cosmetic or fuel industries. And a growing awareness of the versatility of anisole in recent years, as well as its low hazard profile, has been driving market growth for it. Currently, its price ranges between 4 to 11K per ton, depending on the purity and the application. And so while anisole itself is a great green solvent, the way that it's currently made is not sustainable. So at the moment, its production relies on petrochemical resources, typically via the vapor phase alkylation of phenol. And so our first question was, can we instead make it biologically using a microbial chassis and lignocellulose-derived sugars and aromatics as the carbon input into the system? And the immediate answer to this question was not easily. So anisole itself is a natural product. It's often found as a secondary metabolite in fungi and plants, but it's always found in very trace amounts. There's no specific production pathway towards it. It doesn't play a role in central metabolism. And as far as we're aware, nobody's previously attempted to make it microbially. So we had very little chemistry or biology from which to draw on. And with that, we decided to start by constructing a synthetic pathway to anisole using Pseudomonas putida as our production host because it is an organism with really versatile metabolism, and it also has very high solvent tolerance. So to get to anisole, which is here, something that we know about Putida's metabolism is that one of its aromatic intermediates is 4-hydroxybenzoic acid. And to get from 4-HBA to anisole doesn't require too many steps. It just needs a decarboxylation and a methylation. But in what order do these reactions need to occur and via what enzymes, we weren't too sure. There are two potential routes that you can take. In the first, you have an initial methylation reaction followed by decarboxylation, and in the second, you lead with the decarboxylation step. So to identify which route is the better option for our purposes, we started by investigating the decarboxylation step. And here we selected 3 different prenylated flavin-dependent decarboxylase systems that had previously shown activity towards either 4-HBA or 4-HBA-like molecules. And what we found was that none of them have activity towards the methoxybenzoic acid of route 1, but the 2 from Klebsiella and Sedimentabacter were able to fully convert all 4-HBA to phenol. And so that was a decision maker. We'd be following route 2 towards anisole. So once that was established, we then move on to trying to identify a methyltransferase that is capable of acting on phenol. And here we ran into more trouble because there aren't very many methyltransferases that have been reported in the literature as being able to catalyze this transformation. And those that have been reported to do so with very low activity. It's not ever the cognate substrate. But we did identify 4 potential candidates. They're all class 1 type natural product SAM-dependent methyltransferases, and we evaluated them in vitro. And what we found was that the best candidate was the third one down on the list, the MOMT9 from Clarkia, the genus Clarkia. But even so, the conversion efficiency wasn't great. It's only 16.6%. And part of this is by virtue of the fact that this enzyme doesn't have great specificity towards phenol. But we also suspected that a contributing factor is the cofactor used in these assays. SAM is known to be very unstable in vitro, and it obviously can't regenerate itself. So we suspected that once we moved into an in vivo system where it's able to recycle, that we might get better methylation activity. And so then from here, we decided to try moving into an in vivo system. So for this, we constructed this cassette that you see here, which is constitutively expressing our decarboxylase system from Klebsiella and the methyltransferase from Clarkia. But before we could move this properly into Putida, we needed to resolve one small metabolic issue, which touches on something I mentioned earlier, which is that 4-HBA is an intermediate of Putida's metabolism. It's only transiently present during coumaric acid metabolism. So our pathway is going to be competing with this metabolism for this precursor, which is not something we want, obviously. So to eliminate this, we knocked out the POB-A gene, which is responsible for converting 4-HBA to PCA. And then into this delta strain, we introduced our transformation cassette, and we performed biotransformations, feeding in exogenous 4-HBA. And here we tracked product formation, and we found that 4-HBA was very efficiently converted to phenol, which is shown in blue. And we also had anisole accumulation in vivo. So this was a positive first step. And at this point, we decided that we would take a little bit of a step back and consider this proposed production pathway or platform from the context of the substrate or lignocellulose feedstock that we'd be feeding into it and how that might contribute to product formation. At the moment, coumaric acid is the only precursor that contributes to 4-HBA accumulation in vivo. And while coumaric acid is present in lignocellulose hydrolysates, it tends to be in small proportions. By far, the most dominant carbon source are the sugars, which currently our transformation pathway is divorced from. None of the carbon that flows through central metabolism from sugars is able to reach 4-HBA, and therefore none of it is going to be contributing to our anisole product. So to build a bridge into central metabolism, we integrated a foreign gene called IBIC into the strain, which is able to convert corismic acid from the shikimate pathway into 4-HBA. And this allows us to access carbon that comes from very distal substrates and make potentially anisole de novo. So to test if this is true, we then grew up the strain with our transformation cassette on glucose alone, and what we found was that the strain is capable of making both phenol and anisole together. So this was a second bit of good news for us. But because we're greedy, we wanted to push this even further. And so from this point, we were interested in bumping up how much anisole we can make. And for this, what we did is we engineered a genetic strain of Putida with this particular background that you see here. And these modifications are serving three main purposes. The first is to improve cellular availability of the precursors that feed into the shikimate pathway, which is the yellow pathway to enrich coresmic acid. The next motivation is to reduce carbon flux away from the shikimate pathway, for instance, into the TCA cycle. And then the third is to introduce xylose catabolism to the strain. Putida cannot natively consume xylose, but it is highly represented in lignocellulose hydrolysates. And so this particular genetic background was achieved after 6 consecutive strain iterations, which are in the table on the right. And what we decided to do was transform each of these iterations with our transformation cassette to observe how these stepwise modifications impact product formation. And so here are these production time courses. All of these were grown on glucose alone. And what we see as a general trend is an increase in product formation as the strain becomes more specialized and optimized. And by the final iteration, we're making about 3.5 times more aromatic product than the first. But we also have a continuing problem, which you can see in these graphs, which is the persistence of phenol. And so that's telling us that our methylation step is still a bottleneck in this process. So at the moment, what we're doing is we're exploring a broader panel of methyltransferases to try and identify one that has better specificity towards phenol and can close that gap in production. We've also started looking at how Putida performs on different lignocellulose feedstock compositions. So for this, we use design of experiments with a 28 condition matrix with different ratios of glucose, xylose, ferulic, and coumaric acid, and evaluated how these different compositions impact anisole production. What we found was that the best composition was pure glucose, but luckily some of the next best compositions are much more reminiscent of what a lignocellulose hydrolysate would look like, for instance, condition 18. And so these are the conditions or compositions that we would prioritize when we move into scaling this process, which is something that we're in the beginning of exploring. This is some work that we're doing in collaboration with the Winterburn Group. We've been looking at different bioreactor configurations for this anisole production platform. To begin with, we tried replicating what we did previously in Flask, which involves a dodecane overlay in these cultures, but this didn't translate so well to bioreactor. We see persistent anisole loss due to its volatility over time, and also the agitation of the bioreactor kind of whipped the dodecane into a bit of a cappuccino foam at the top, which limited accessibility and product recovery. So from here, we then tried a different configuration where we have dodecane just in the scrubber to capture anisole from the off-gas. But again, we see persistent anisole loss, so this would solve the cappuccino froth issue. So at the moment, we're looking at different capture solvents to try and find one that is able to hold on to anisole better than dodecane is before we move into production properly. So then the last thing that I will tell you a little bit about is something that Rosa touched on because it was in collaboration with the Cuellar Franca group. What we would like to do in the future with this study is explore the real-world impact of a biological route to anisole. And this is a previous study that where we looked at how a consolidated enzyme hydrolysis and microbial valorization of municipal waste-like feedstocks to make bioplastics performs both environmentally and economically prospectively. And here what we found was that a biological valorization route like this can reduce CO2 emissions by up to 62% while having cost parity with current waste treatment options like incineration for energy generation. So this is something that we're looking to replicate with our anisole platform to identify what the major climate impact issues are and key sustainability points that we can improve on. So things like media or solvent recovery and recycling and the energy demand of the system. And so, yes. I'll end there with this.
Any questions for Micaela?
I have a question that might be something you've already tried, but you know when you were talking about the scrubber and trying to capture it from its volatility, did you think about fitting a condenser on and just trying to cool it so you could capture it as a liquid?
I didn't perform that particular work, so I'm looking at James.
Yeah, very quickly, yes is the answer. We did, and perhaps we can talk more later, but you've got such high kind of airflow rate through the system to meet the biological oxygen demand that in very crude terms that gives you a lot of like removal power. Yeah. So you're just removing, and even if you capture, you just strip it out of the solvent again. But yes, in various kind of extremities of things that would never really scale, but you're just trying to prove the concept in the lab.
Oh, thank you.
No, thank you.
Any other question for Micaela? No? I have time. First of all, well done for working with Putida, because that smell.
It does. It really, really does.
You bring memories back that I really didn't want to. Putida is not the most. Glucose was the one that gave you better yields.
Yes.
Glucose is the preferable carbon source for microns, so that wasn't expected.
No, it was not expected.
Yeah. So have you looked into producing with different carbon sources that come from different feedstock, renewable feedstock, waste streams, or is that in the pipeline, or is something that you're going to look at?
So this was quite a preliminary look at different compositions, just to kind of have a broad view of how sugars versus aromatics contribute to product formation. It is something that we could expand with more sugar options, different types of feedstock waste substrates.
Sustainable feedstock, sustainable ionic liquid, replacing organics is a full package. So well done. Thank you, Micaela. Our last speaker for session 4 is Joseph Ince from Marble Beers. Joseph has over 15 years experience as a head of production in the beer sector. So far, we have listened academic showing their core research, which has been impressive. This time is looking from the other side, from a commercial partner that works on academia and how the journey has been. Thank you, Joseph.
Hi, thank you for the introduction. As Ali said, my name's Joe. I'm from Marble Beers Limited, which is a brewing company in Manchester. We make beer and sell beer and do that. So I have approached IBIC from the side of a SME, essentially. So I think I'm probably the first person speaking today that doesn't have doctor or professor before their name, which is quite interesting and quite intimidating to be here. But yeah, a lot of this research goes on to industry. We approached it the other way and basically came to IBIC and came to the University of Salford saying, we have an idea, but we don't know what to do with it. Can you help us? That's the wrong way, which is a great start. So our brewery was founded in 1997. It has moved from Manchester to Salford, which is, two of the bigger cities in the northwest. We have an ethos or an MO or a mission statement or whatever of quite purposeful, slow, organic growth. We are not rushing to get particularly big, particularly quickly, although I have dreams of farms and chateaux in the south of France and a Porsche at some point. We currently employ around 30 staff between our sort of brewing and production site and our on-trade premises. We're set to produce about 5,500 to 6,000 hectolitres this year, which is, about 1 million pints. So we are a very big, small brewery, and quite happy with that. We very much fit the SME, scale, I would say. See if my notes match my slides. So at the moment, the sort of UK craft brewing or small brewing industry is facing a pretty tough time, as is a lot of manufacturing in the UK. some of the things we're sort of facing are increasing energy costs, increasing costs of raw materials. So while we're always looking to sort of innovate and move forward, we also have bills to pay and people to pay and a business to keep running. So while we wanted to develop something that was sort of lower cost, more efficient, and innovative, we needed to come to academia to help us do that. We can't run tests in site. I can't give up a ton of capital to go through an idea or plan something that isn't going to work or isn't going to work quickly. Which brings on to our idea of sort of sustainability. So we want to do better for the environment, but also better for ourselves. And we can't go all out and become super green or do like an LCA process and then run out of money a week later. So do a little bit of sustainability today, a little bit tomorrow, so on, so on. Craft brewing, as you're probably aware, is quite a biotech intensive business. We use sort of 4 base ingredients of water, malt, which is cereal, yeast, and hops generally. When we sat down with the guys from Salford and IBIC, we really wanted to focus in on the area of hops. So the 2 people we were working with from Salford are very into biotransformation. So we took the idea of looking at our most expensive by weight ingredient and then how can we reduce its use using biotransformation. So we wanted to look at the way yeast cells take up some base materials and turn them into things that are present in hops and where we can sort of go with that. This would enable us to keep product quality, which is quite important to us, but reduce our costs and also sustainability in the agricultural. We do it. Pretty much just covered this stuff. Here's a yeast cell. So phase 1 of our introduction to Salford and IBIC was based on a little bit of cross-training and talking to academics and researchers who have very little idea about beer or product manufacture apart from what they would see in a glass or taste, and sort of talking to them about flavor qualities that we really want in our products or that we have in our products and flavor qualities that we don't want, because sort of initial ideas were, well, you could just put loads of this, like loads of luminol in, and that would give you a really flavorful beer and this, but those things then come with negative flavor combinations that we don't particularly want. And something that's quite important to us as a business or as a producer of a food product is consistency of product type as well as sort of product quality. So our research relationship development, or phase 1 of sort of working with IBIC, was to cross-train. We sat down, we taught them about off flavors in beer as well as positive flavors in beer. We did this through a sensory panel, so that's something that working in breweries is quite common for me to do, something I do every few months and have done since I started brewing, where we teach people how to taste beer, how to smell beer, what they're looking for, what they're not looking for. I forgot to pre-warn the people we were working with things about like sensory blindness, so please don't wear perfume, please don't drink coffee in the morning, please don't have lipstick or makeup on, please don't have anything, please be as blank and as neutral as possible. So that was also a valid learning experience for me of how to communicate with people outside of my profession and what to expect from them as well as learning, which was really good. From this we've moved on to phase 2, which is initial product development. I'm not going to pretend to sort of know what this graph says. I'm sure everyone else in this room can read it quite well or better than I can. But what I'm told is it shows the things that I am looking for. And basically that the concept or that the idea we've had has merit to it and is valid, and that I should then propose the next sort of set of tests that I'd like looked at or other sort of raw materials that I think it's valid for us to look into. Which then, leads us to our next steps. Having been given sort of a base set of data from IBIC that I'd had an idea about, but no validation for it. It was nice to get results back in data back that gave us validation that our theory was sort of correct, that we can now go on and look at full-scale brews producing actual commercial products. We can look at testing combinations. So we had a base idea of some raw materials we wanted to use. This can now be expanded outwards. And we can engage other stakeholders. So where could we find these raw materials? Do we want to share these sort of ideas with other breweries, which I think would be really cool? And could we take this on to other, maybe non-beer brewing, but food products that use fermentation, so kimchi production or sodas or hop-based sodas. And I think that's about it. So yeah. So the basis of the talk was to say, if you are in industry or an SME in here today, go find a university, go find an academic, go get funding, have an idea. They're quite friendly. They're quite open. They quite like it when you say, I think you could help me get funding. And if you are an academic here who wants to reach out, you don't necessarily have to go to Unilever or BP or someone massive. You can come and work with an SME. We will rely on you a lot more for input and stuff, but SMEs are here to be used, and there's quite a lot of us in the Northwest. Thank you.
Thank you, Joe. Any questions for Joe?
I work with innovation companies quite a lot. So people from universities can imagine, well, we have some kind of real world application and not to industry. At the same time, I also work with SMEs who then come to me and say, I don't think this is for us. That kind of innovation, that kind of level of technology, perhaps, that kind of level of process, not for them. So for yourself that has used IBIC as an innovation catalyst and successfully integrated learnings into your business, give me your top tips. How to manage this relationship between two parts that don't seem to be.
So
One to work with each other.
there can be a language barrier. So, and it's also I think a very early set of expectations. What is the SME expecting to get out of it, and what's the research base getting to go out of it? And then you can be honest and ask why is this not for you? So there's other grants and other things we've looked at, or either in other IBIC sort of projects that we could have put forward that we sat down when we talked about it. I was like, I haven't got time for this. I have a business to run. I barely have time to do that. I cannot sit and write your research project or your method for this. I have come to you with an idea. Please go away and do it. Please don't send me 15 emails. Please send me one per week, and we will attend it, and we'll attend meetings. So I think if you want to approach SMEs, ask them what their barriers are, and their barriers are going to, I can tell you before you've asked them, are capital and time, and then training. So sort of phase 3 of the IBIC for us would be looking at this comment fund. So we could then go out and say, find new products to use, but I can't just go to the university every 3 months and be like, can you test this for me? Can you test this for me? So one of the things we want to do is bring that knowledge in-house. So get guys from the university to train our guys on how to use it, how to use the equipment, what equipment to buy, how to maintain it, so we can then do those things for ourselves. So yeah, if someone says no, ask them why they've said no, and then go to their competitor. But it's an open place, right? There's very, especially with an SME, there's not one business doing one thing. So you can go, I keep hitting them. There's a lot of places you can go to for that. And yeah, you might have to knock on 5 doors, but you only need one to open, right?
The question really, are you looking for more beer tasters?
It's really not fun. It's especially not fun when it's 7 o'clock in the morning and 95% of what you're tasting is this bad? Yes, it is. Yes, it is.
Well, you make my favourite beer, which is Manchester Bitter, so I'm sure I'll come.
Well, thank you. That's very high praise. Is there anything else?
Yes. Maybe this is a question to the room, because on the academic side, we don't see some of the problem statements or challenges that SMEs are facing that maybe we could help out. So is there a way that you can sort of share these challenges and then find an academic?
I think so. I obviously can't answer for every business in this room. Another sort of funded project I worked with that was through the University of Salford is called NERIC, and it's for automation and robotics. And I went to them thinking I had a problem with our canning line, and I didn't have a machine called a depalletizer, and I didn't have a inline weigh station that helped me reject products that didn't hit a base QA level. And they went and looked at our process, looked at what I wanted. They were going to help me source it and find really good ones. And then they looked at it and said, oh, actually, that's not where your bottleneck is. Your bottleneck is over here. So that was really interesting for us that I went to go and get advice on what to buy, and they actually told me what not to buy. So I think as a conclusive sort of area, that probably, I don't think there is a list where you will find 50 businesses have written 50 challenges that they face and they want to look into, because you're way more specialised than that, and businesses tend to be way more specialised than that. But you can go and look at the area you're interested in and then go to a local business that is involved in that area and say, have you thought about this? Because I didn't know about any of this stuff till like 3-4 years ago, and I really started looking for help and looking at what was around and available. So I guarantee you there's businesses in your like area of specialties or your area of research that might not know that you're there. They might not be the gold standard or necessarily one you would want to work with or for, but they will be out there.
There's one thing I wanted to mention. AIM Day. So I attended an AIM Day that was supported by IBIC actually. And the format of the event was an SME would come with a problem that they're facing in their business. And the AIM Day organisers would just have a bunch of academics and people from consultancies and such, as myself, and sort of just sat there and brainstormed for 45 minutes to try and do a problem. And try to do that's how
Yeah, no, that's really handy and something, I probably could have done with about 5 years ago.
Can I just come back with that? I think we kind of, within IBIC, we call them innovation labs. We had our first one on biocatalysis last week. So if there's anyone in the room that has got challenge area for us, we're more than happy to put on one of the innovation labs, which is effectively a half-day facilitated sandpit event, and we have money at the end that catalyses these solutions that you find during the brainstorming to the challenge that you come with as a company. So okay, great.
That's fine. From the academic and the other side, I would say communication is the key. As Joe said, the language, I couldn't understand a word of how they make a beer or the ingredients. Thank God I got a translator in that table. But I was one of the persons sending 15 emails a day that they are not going to read. They are not going to read. There's no way, because they have to produce something. We expect them to do that, but the reality is it has to be like a halfway there. When we, instead of 15, you send 3, and after the 3 you ring, because you know that they will pick up because it's urgent. But the other way around, as an academic, we cannot expect them to react in the same way, but help them to innovate on the space. So thank you, Joe.
Thank you.
This is our last talk for session 4. Now I'll welcome Phil, session 5.